Thank you.
Yes, thank you very much, and thank you for having us. So today we're going to present the workflow that we applied for the E18, E39 Gartner project, and how we managed to extract data from Quadri to do our structure models in Tekla, and then push it back to the common data environment. So my name is Augustin. I'm a computational design lead in Rumble, Finland, for the major projects department.
And hello, my name is Tom. I am computational design engineer in a major department, also in Rambo, Finland.
And of course, right now it's just the both of us presenting this workflow, but we are presenting on the behalf of many other people who are still working on the project. So this is obviously a team effort that is led mostly by the teams in Finland and in Norway. So a quick project introduction. This infrastructure project is located in Kristiansand in Norway. And the scope of the project is the reconstruction and upgrading of a heavily trafficked transport corridor that connects the E18 highway and the E39 highway. So the project will improve accessibility, reduce vulnerability, and increase safety at the junctions of all these different roadways. And it will include intersections with tracks, railway tracks, the construction of new bridges over railway, the constructions of many retaining walls, and other infrastructure projects. The total length is 1.4 kilometer for a total cost in around 533 million, and the development started in 2021 and is supposed to open in 2029. So this is an ongoing project, and we're definitely full steam ahead when it comes to the production. So if we have a look at what we've been working on, it's mostly the structures and the infrastructures. So this is an overview of the project, and now we can have a bit deeper look in the different structures that we have. So in total, we have around 15 bridges and more than 30 retaining walls. Most of them are mechanically stabilized walls. The urban and topographical area or setup is quite challenging because it's a very tight environment with a lot of different elevations. So the geometry for the different structures is very challenging. We have curved bridges with variable cross sections, different retaining walls that needs to connect with these structures. So it's definitely a challenging area. We have complex alignments that are changing quite often because of the sheer density of the structures that we are building here. And the idea of the project is that the bridges and wall axes are all controlled by a shared reference geometry from the central alignment model, so Quadri. And all the geometry for the bridges and the walls is parametrically defined, which allows us to update consistently all our models when the road alignment varies, which is inevitable in this type of complex projects. So this is, for instance, an overview of one of the bridges that connects with retaining walls. So this is a pedestrian box girder bridge. Then we have this extremely massive mechanically stabilized wall, which is around 50 meters high. We have, for instance, two bridges that are going over a tunnel, which is always something fun to design. And I think that represents quite well the sheer complexity of and density of the structures that we have here. We have also some bridges that are curved in any possible direction with variable cross sections in, again, any possible way. So definitely the geometry of the project is very challenging, and the workflow that we're going to present now kind of supports a bit this complexity, or helps us to deal with that complexity. So really, the challenges that we have to face in this project for the structural design is that, first of all, we're in Norway, so this is a drawing-less delivery. So we are shifting from a 2D documentation model and using the model as a single source of truth, which means that we need to have very precise models for the validation and the review process. Just to give you an example, we have more than 132,000 data entries for one bridge model. So we have a huge amount of data to handle for each structure. I have to mention that this is not entirely drawing-less projects, because for each structure we might have up to 6 drawings, compared to probably the 100 drawings that we would have to do in a say traditional setup. So this is still quite significant reduction in drawings. We have a very high level of details also to deal with. So all the components in the models are fully modeled and attributed. So in some models, we have more than 30,000 objects into one model. All this model needs to be clash free. We also need to model the non-geometrical data to be able to convey information that would be traditionally represented in drawings. Third aspect or third challenge is that we are working in an integrated workflow. As I mentioned earlier, we are dealing with a very tight area, which means that we also need to be tightly coordinating with the other disciplines, whether it's road, drainage, geotechnicians, structures. We have consistent data pipelines that have been established to our common data environment. So it's a collection of different applications such as Quadri, Trimble Connect, and project-wise. And we are also handling very frequent design iterations, and we need to maintain the data integrity across these variations. So really the challenges are the amount of data, to try to keep the data consistent, and also to try to automate the model creation to be able to handle this amount of data and the amount of changes across the projects. So I really felt connected to the keynote this morning when they said that the future is data, data, data. So this is just an example of a final output that we have for one of the models, where we have quite many attributes, as I mentioned, and then everything, and when I say everything, I mean literally everything, is modeled or is represented into the model. So this is quite a lot of information to deal with. So if we have a look at the global workflow of the project, because this is what we are trying to present today, this is how it looks on a very, very high scale. So this is the high level project workflow that is common for all disciplines. It includes various automation tools, multiple design softwares that are all federated to one common data environment, in our case, project-wise, and some other subsequent common data environments. That is supplemented, of course, with Trimble Connect to help us interact with this data and visualize this data in a nice 3D world. But this is, of course, a simplified representation. If we have a look at how the workflow looks for structures, it would look more like this. So you can see that now things are getting a bit more complicated. We have a lot more data entries and ways to interact with information. But essentially, these charts here represent at the same time the bridge discipline workflow, or the structures discipline workflow on the one hand, and then of course the multiple discipline workflow. And the idea is that we're going to follow the workflow along and look at different aspects of the workflow and see how we are dealing with the data and interacting with the data. The first step is to prepare the initial data, make sure that we have the initial data that is clean and ordered and organized. Second step is to automate the model creation and to integrate or to integrate it within the workflow. Third step is to actually push data to the model. So we create the geometry, and then after we add a lot of information to that model. Third step is to make sure that our model is of good quality. And then, of course, we need to push that model to the data environment to process the model, to send it to the combination models, to make sure that all the project stakeholders have access to the information and have access to good quality information and the information that is relevant for them. Because we are creating a lot of information, but of course, that information might be of relevance for some people, but not of relevance for other people. So the post processing takes care of stripping down the information that might not be relevant for certain stakeholders. First step, of course, is the initial data preparation.
Thank you, Augustin. This is my part. So this is the first step in our workflow, the initial data preparation. So it's important because we collect all the necessary data for bridge modeling. So we use the three main pieces of software: Quadri, Tekla, and Trimble Connect. Technically, they can exchange data directly with each other, but we still use Rhino and Grasshopper at the central hub. This means the data is stored and processed inside Rhino and Grasshopper. It helps us control the workflow and keep version history and check change more easily. So we also have a quick way to check model from Quadri to Tekla, but I will explain that a bit later. And now let's have a look how I prepare the data. So I create the different tasks to collect all the necessary data for my project in Quadri. This step help the organizer input data clearly before bringing it into Rhino. So we have an input file that includes the data I got from Quadri before. These files include important information such as the alignment, row surface, existing ground, or other basic geometry needed for the bridge model. The data as handled by type, together with some metadata and extra information added by user. So we also use chain detection in the script. It compares the data that were back before with the new data going to Rhino to detect any change. So the chain are also directly so in the both model and script. Zip help user quickly to see what has been updated, so they don't waste of time to checking everything. So I use this function in almost every script because it really save a lot of time. So you can see in the slide here, green means no chain, yellow attribute chain, red is geometry chain. So I always feel comfortable when my script show green or at least yellow. It red, if it red, it means something need to be checked or updated. So for the bridge side, we use the data from Quadri. But it doesn't need to editing or change. But however, the MSC Word, there is an extra pre-processing step. This is because MSC Word connect the rows, tunnel, bridge, and other structure. So their geometry need to be carefully aligned before modeling. So you can see this solar line were imported earlier with the color code to indicate the which side is which because it's important. It affects to the how we model the returning work. So based on the spot file, we process the existing line to improve the geometry and make the connection smoother. So after cleaning and organizing the curve, they are ready to automation. So, and here is you can see the final geometry after processing together with the reference model. So as you can see, it looks quite massive. So after we have all necessary data for modeling, we move to the next path, bridge integration and automation. Here we use a spot file, so our single point of truth. So for both FAM and beam side, we have just one file as input, keeping everything consistent. Whenever the spot file is updated, the data is automatically updated for both FAM and beam. Along with the spot file, we also use the master precision for both FAM and beam. When it's created, it changes how we model and making the process faster and more efficient. The master question store a lot of information for both systems. Each point in the master question have relationship with other and store in JSON format. So it's easy to read and FAM only need to create it once and Beam can use it directly. So and finally, after we have finished everything, we export model to Tekla. So we use one script for geometry and another one to export to Tekla. There are also separate scripts for different structure, such as the railing, accessory, superstructure, substructure, and so on. You can see exporting the railing right now, step by step, to make sure everything works correctly. And for reinforcement, we aim to use only one script and the same input format in spot reinforcement Excel file for entire structure. So the script can be reused for different structure paths, including the deck, abutment, foundation, column, and etc. So uh, beside checking the script when we build the model ourselves, we also need to verify the model after exporting to Tekla. So in the project, we also use additional quick check based on data from Quadri. So as I mentioned earlier, we can also transfer data directly from Quadri to Tekla using a similar method as for Rhino import task. For example, in the case we export the alignment and row survey from Quadri to Tekla and then overlay them. So with the bridge model to check if the station position are correct or resource survey match or not. So I also added the other data to model for measurement and sketching. As so in the picture, we can also select which geometry to export using the Quadri corrector, and the Quadri corrector also support exporting vertex back to Quadri, but we didn't use that feature. That's all of my pass. Thank you for listening.
Thank you, Tung. So now we managed to create in a certain automated way a model with geometry, certain attributes. But as I mentioned earlier, since we are drawing less, we have a lot more attributes that we need to push to the model. And in order to be able to do that on these many structures in a very consistent way, the first step that we have created is a data dictionary. The data dictionary allows us to classify the attributes that we want to push to the model. So we have a list of objects, we have a list of attributes, and we can establish relationships between the objects types and their attributes. So this is a very flexible system that allows us to be able to assign proper attributes to the proper objects, map the attributes to the various design environments, whether it's the Tekla UDAs, whether it's the Quadri attributes, whether it's the attributes that we use in Rhino and Grasshopper. We have those different mappings available to us to be able to push those attributes in the right location in the different models. This also, for instance, allows us to learn Norwegian because neither Tung nor I are from Norway. So we had this data dictionary that helped us to be able to push the right attribute into the right location, even though we didn't speak the language, because then we have access to additional metadata about each attribute. So in an international environment, well, we need to deliver structures in a local environment. This is extremely valuable source of information, a valuable way to harmonize the data for all the project actors. So then the next step is to what we call enrich the model, which means that basically we have huge amount of data that we need to push to each model object. So the enrichment phase is a workflow that connects Tekla and Excel through unique IDs that we've created for each object to make sure that we have a smooth data exchange between those two areas. We tried to use the Tekla native features for that, but unfortunately they weren't allowing enough flexibility for us to be able to deal with this many attributes. And now this workflow allows us to automatically fill or update the UDAs in Tekla based on values that are stored in Excel. We can also read the data back from Tekla to Excel to be able to keep both sources synchronized. The second advantage is that it allows us to have people who are not Tekla users to be able to start to insert data into the Excel. Everybody's familiar with Excel, and then our BIM modelers are able to then get that data and push it directly to the models. So it gives us a bit more flexibility when it comes to being able to insert information into the model from all the project stakeholders. So it's a very valuable aspect that if you want to add data, you can just do it yourself and add the data in exactly the place that you want instead of relying on a third party BIM modeler to be able to do that. So now, for instance, we have quite a lot of safeguards that allows us to interact with Tekla through Grasshopper with different coloring aspects that tells us that, for instance, some objects have been created in the Tekla model that have not been referenced yet into our attribute spreadsheet, so that we need to reference them first. And then once all the objects have been referenced, then we can start to push the attributes to the object. We have a step-by-step script that allows us to make sure that we will push the proper data to the proper objects. As I mentioned earlier, we have huge amount of data that we need to push to the objects, so it's paramount that we have a very granular level of control on the data that we push before we push it. Otherwise, this is how you mess up with your model. We are trying to automate the attributes creation, but that means that if there is a mistake, we can potentially also automate the mistake. So that's something that's important to keep in mind. So now that we have models that are automatically created and fully attributed, the next step is, of course, to make sure that those models are up to quality standards. So we've been using Trimble Connect and the Trimble Connect organizer very extensively to be able to do this QA. It's important to mention that we have our own Trimble Connect for infrastructures. That is not the one for the common data environment, so that we can do our dirty laundry, as we call it, before pushing it to the command data environment. We use then Trimble Connect Sync to be able to send the data back to our own SharePoint to have also access to those files in different platforms. One of them is, for instance, Solibri. We've used also Solibri to be able to do rule-based QA because since we have so much data, quite a lot of these data fields can be checked using rule-based, which allowed us to be a bit more effective in checking all the data. We are hoping that we will be able to use IDS in the future. We haven't done that yet, but I think if we can try to use building smart recommendations such as IDS or BSDD for the data dictionary, those would be very valuable add-ons to our workflow. So now let's say that the bridge model is accepted and validated by our internal QA, we can push it to the outer world. And for that, we have a huge helper, and this is called the Beambot. So the Beambot is responsible for the multidiscipline model processing. It means that it has scheduled exports from the design softwares, whether it's our own internal Trimble Connect, whether it's Quadri, whether it's any other design softwares. It takes care of the syncing between those different federation models, our internal Trimble Connect, the project wise of the project, the Trimble Connect that is used by all the stakeholders. It creates master models. So this is what I discussed about earlier, that we need to be able to clarify the information for all the different project stakeholders. Not everybody needs to have a look at all the reinforcements that are modeled on the bridge. So these master models are trying to strip down and simplify some of the models for the global coordination. And also it takes care of the versioning and the tracking of the changes and being able to communicate the changes. So if we look a bit under the hood, how it looks like, almost each step of the workflow is monitored through this change detection, and the change detection then triggers the updates and the actions when the models are changed. So some models are still uploaded by hands, usually coming from other disciplines and external consultants. So it can be, for instance, landscape, electrical, district heating, so on and so forth. But then once we are part of the ecosystem of the Beambot, the first step is that our models from bridges and retaining walls are uploaded to ProjectWise. And then second step is that we use Quadri and Quadri Nova Point to be able to process these models. So the first step is to import to Quadri these simplified models, maybe strip down of the reinforcements to be able to have like a simplified geometry. Then these ones are re-exported back as master models. That's the step 4, to be able to have like a very easy model to deal with, where we can have a look, a holistic view at all the structures that have been designed. The Beambot also takes care of exporting all the road discipline models, so the roads, the signage, the drainage model from NovaPoint and Quadri as a authoring software back to the command data environment in different formats. We've used LandXML, we've used DVGs, we used IFC and TrimBeam to help with the visualization process. The Beambot takes care, as I said, about the master model creation. And then once all these intermediate steps have been created, it pushes updated models to the shared environment, in that case, the Trimble Connect, that is shared with all the project stakeholders, the client, the contractor, the validator of the structures. So there's a lot of stakeholders that have access to that Trimble Connect and that have access to those simplified models in order to be able to have exactly the level of information that they need. Um, and last but not least, the Beambot posts a digest on Teams internally, so that we have all the time situational awareness of what has changed within the project. We have many designers working on a project at the same time. We need to be made aware when some of the references that we use may change. And the beauty of the Beambot is that it's working when we sleep. So next day when we come, it has done all this work in the background for us, and we have in the morning a very nice and clear summary of what happened in the models. So this was the presentation about the workflow. There is a lot that has been said, but if you can maybe focus on few takeaways, is that first of all, on the workflow and the process, we managed to have an end-to-end model-based workflow that relies on not only on files but also on objects, and we are able to pass objects from one place to another, from Quadri, then to Tekla, and then from the data dictionary to Tekla. We are also heavily still based on files, as the Bimbot mentioned, but we are still able to manipulate those objects within the files. The automation really reduced manual exports and improved data consistency. And we managed to standardize the data structure, which allowed us to have an easier collaboration within the team. But it's a very complex workflow, and there's still some challenges about the data consistency when we access to these data points. For instance, in Quadri, we need to make sure that everybody follows the same procedures, and that's actually quite a challenge. On the learning and development side of things, I have to admit that this is a very steep learning curve for new tools and new scripting workflows. So we need quite heavy training and onboarding to be able to have our teams running the workflow properly. And we also need to have a clear ownership of the automation processes, so that each individual is responsible of the output that the script that they run. Even though the script that they are using is not by them, they're still the owners of the output of that script, and that's also quite important in a heavily automated environment. On the coordination and integration level, I think this really allowed us to enhance the coordination between the road, the bridges, the retaining wall design. We have a very tight environment with lots of geometrical connection to deal with. So this workflow allowed us really to be able to focus on this synthesis and the coordination between all these different aspects. It's still sometimes challenging to synchronize the attributes definition across the disciplines, but then within each discipline, since we have this very strict workflow, it's quite helpful and powerful. The consistency across the discipline might still be an issue, but it's still going in the good direction. And on the outcome and impact, I think this really improved the quality of the deliverables, especially considering the sheer crazy amount of data that we are pushing. Especially, we had some significant time savings, especially on the walls, because these are very, very replicable structures, which means that the automation and the scripting combined with this way of pushing the data and handling the data made things very, very powerful in being able to just mass produce those walls one after the other once the geometry has been set. For bridges, we've had mixed results where, depending on the individuals, the teams that you have, the skills that we have, we've had some very, very efficient and agile processes, and sometimes also some pitfalls. But so the workflow remains heavy and requires dedicated maintenance, but altogether, it's a very powerful workflow that I believe has a quite powerful future. Thank you very much.